Well, thank you all for joining another lecture for Introduction to Computer Graphics. We're going to continue talking about ray tracing today. We're going to talk about a bunch of interesting stuff related to ray tracing. But we're going to start with shadows, right? So, what are shadows? So, let's say that I have an object like this, a sphere. Are there shadows here? Are there no shadows? What do you think? Is there any shadows here? Maybe. I mean, you could say that maybe the back side of this sphere is in shadow. Maybe, maybe not. Okay, so how about this? This is an obvious shadow, right? So what happened here? All of a sudden, you look at the sphere, and you can tell that there's something underneath this sphere, right? Something underneath this sphere, even though I'm not showing you that there's actually a plane here. You can actually tell that there's a plane. But what is it really? What is this black thing that we call shadow anyway? And this is important to, I mean, this is sort of obvious, but it's important to understand this because that's going to be how we're going to compute shadows, right? So what is shadow? The shadow is, you can say, the absence of light, right? But it's the absence of light in the presence of light. So there's got to be some light for us to have some shadow. No light, if there's no light, there's going to be no shadows, right? I mean, shadows appear because there's light and a part of our scene receives the light and some part of our scene does not receive this light, and that's where we have shadows. So it's all a part of this light. We gotta have a light source. So by looking at this shadow, you could tell that there was a plane, and you could pretty much tell where this light was supposed to be, right? It gives us this clue of where this light is supposed to be. Also, like probably the highlight on the sphere is giving you a hint about where this light source is supposed to be. But the point here is that shadows are very, very important, and very, very important to compute relatively accurately, because it gives us some idea about where things are in our scene and how they're oriented together. Like, for example, if I just remove this shadow, look at this. What happened here? Now look at this sphere. Does it look like it's on this plane? Not quite, right? It just doesn't really belong there anymore. So shadows are very, very, very important to get right. There are certain things in computer graphics that may not be very important, but shadows, they are actually important. We need to get them right. So we said shadows are related to the light source, and we're going to have shadows where the light doesn't reach. So what does that mean? So let's pick a point in the scene. Let's pick a point on this plane over here. That I picked a point. Is this point in shadow? Well, if the light can see that point, or if I can see that point if I can see the light source from this point, then the point is not going to be in shadow, right? So what I'm trying to say is that if there is nothing between this point and the light source, if this line segment is not occluded by anything, then this point is not going to be in shadow, right? But if I pick another point where this point will not be visible from the light source, such that if I draw a line segment from this point to the light source, it's going to be going through an object. That means that point is not visible to the light source because there's some other object in between here that's blocking the light, right? So the light cannot see that point, or this point cannot see the light, or the light from the light source is not reaching this point. That's why it's in shadow. That's a very, very simple idea. I'm pretty sure you all are familiar with the concept of shadow, so I'm not going to spend too much time on it. But by doing this test, by checking if there's anything between the light source and the point, we can tell whether or not that point is inside a shadow or not. And that's exactly what we're going to do using ray tracing with shadows. It's going to be ray trace shadows. Right. The idea is very, very simple, and ray tracing will allow us to do that very easily. So let's say that I'm rendering a scene. I have this camera, all right? I put this camera here. I could put it anywhere. Let's say that I'm rendering the scene with ray tracing. So I'm sending a ray from my camera. That's going to be my primary ray, all right? And then the primary ray, let's say that it went all the way and hit that point that we were looking at previously. So to check whether or not that point is in shadow, all I need to do is to generate another ray and trace it. So I generate another ray starting from that point. And I'm going to trace it all the way until it reaches the light source. So if that ray reaches the light source without intersecting with any other object in the scene, that means the point is not in shadow. But if it intersects with any object, in this case it's intersecting with a sphere, that means that it is in shadow. It's very, very simple, right? And so this kind of ray, we're going to call this a shadow ray. Right? It's a special kind of ray. It's used for checking whether or not we're in shadow. Now I'm going to talk more about shadow rays and other types of rays and how they differ, but we'll talk about it later on. So let's say that this special kind of ray is a shadow ray, right? So simple enough, conceptually very simple, right? I mean, this is what today is going to be all about. Really, last time we talked about the math of ray tracing. This time we're mostly going to talk about how we use that math to do things with it. So computing shadows is just one of them. Very, very simple. I'm pretty sure you all can implement it. I mean, if you can't implement ray tracing, if you can generate an array and trace it, you can trace a shadow ray, right? It's not that difficult at all if you are able to trace rays in the scene. So if you just do this and implement this properly, you would expect to get a nice shadow like this, right? But what you would actually get would look like this. Oh, wait, what happened here? What is happening? We wanted to get this. We're getting this. What is this? Do you see these? They're little streaks here, sort of. Like, I'm not supposed to have any shadows here, but I'm getting these shadow streaks, right? I'm not getting this. I'm getting what is happening? Something strange is happening, right? Yeah, if you just it's a bug. It's not quite a bug. This is what happens if you just blindly implement shadow mapping without quite thinking about it too much. Let's see what's going on here. Let's see what's going on. All right, I'm going to show you the side view. So what happened here is that I traced my ray from my camera. I found this hit point, and then I decided to trace a shadow ray towards my light source, and I traced it all the way to the light, and then I'll decide whether or not that this ray hit something and if I'm in shadow, right? So all I'm checking is that if this shadow ray hits anything at all. So starting from this point on this surface, I'm tracing my ray until it reaches the light source and check if it hits anything at all. Here's the thing. I'm going to zoom in here, right? Just let's zoom into this area. Let's zoom in some. All right, let's zoom in. You know what? Let's zoom in some more. Oh, wait, what happened? What just happened? This point is not on my surface. Like, why is it not on my surface? It was supposed to be on my surface. I just zoomed in. What happened here? Why isn't it here? Why isn't it on the surface? Lack of precision. That's right. Yes, rounding error. Yes, so I have whatever floating point representation I use, I am going to have a limited number of bits. That means maybe I wanted to represent this exact point on the surface, but I cannot represent any position exactly using finite number of bits, right? I'm going to pick the closest point that can be represented using my floating point representation, whatever it is that I'm using. Well, typically I'm going to be using 32-bit floating point values, using IEEE floating point format, but it doesn't matter what you use. You're going to have a limited number of bits. So you won't be able to represent a point exactly. You're just going to pick the closest point to it. There is that. There's that. But not just that. Not just that. There's also all sorts of computations you've performed to compute this point on this surface. And those computations, you probably use some floating point representations for those computations too. So while computing the position of this point, with every one of your computations, every time you're doing some multiplication, addition, or whatever, you're losing some precision, possibly, right? When you have multiple computations, one after another, after another, after another, all these small, tiny little errors you make, they might accumulate. And as they accumulate, you might be off of this surface a little bit more than what your floating point rounding error would get you. So there's, yeah, floating point rounding error here because of the precision that you're using. But there's also other factors because you had limited precision with all of your math operations, right? And all these errors you made accumulated and you're not exactly on the surface anymore. You're sort of a little off of that surface. So this point might be above the surface, in which case it's fine. If it's above the surface, I don't have a problem. But if it is below the surface, that's when I'm going to have a problem, right? Because that's when I'm tracing this ray, what am I going to do? If I trace this ray, starting from this point, I am going to find an intersection right over here. Yeah, so I'm checking if there's anything between this point and the light source. The answer is yes. There's the surface. But I am on that surface. I don't care about this surface. So, what do I do? One thing I could do is that I could just ignore the surface, right? I could say, oh, you know what? I'm on this surface. I don't care. I'm just going to ignore the surface. Well, this might be possible to do in some cases, but not always. Depends on what kind of surface this is. So if this is a sphere, maybe it's okay. But if it is any type of concave surface, it might be shadowing itself, right? So I can't just ignore this surface and say, oh, it's not going to cast any shadows when I'm tracing a shadow ray from this surface. Because surface might shadow itself, and this might be something that I actually want to get, depending on how I define this surface. So just simply throwing it away is not a solution that will work in every case. In some cases it will work, but not in all cases. Also, it's a little clumsy because every time I'm tracing a shadow ray, I kind of need to figure out, oh, where did I start this ray and where was I, which surface was I on? And there are a few other edge cases where this might give you a little bit of trouble. So yeah, that would work in some cases, but not in all cases. So, we're going to ignore everything behind the ray, right? We don't care about that part. So we're going to start counting from this point on, but we don't have to start exactly at this point. We can start a little further out. And we can ignore intersections that are too close to this point. So basically what we're going to do is that we're going to ignore intersections that are too close to this origin of the ray. And we're going to start counting intersections from a different point. Let's say over here somewhere. A point that is going to be outside of this plane. with some epsilon, if you will, right? And this is what we call bias. So we're going to add some bias to our ray tracing. And we're not going to look at intersections that are happening in between here. And the way to do that, the way to implement is actually very, very easy. So you can think about, oh, I'm going to take this ray and just move it just a little bit and add more floating point operations on top. No, you don't have to go there at all. This is actually super easy to implement. Super, super easy to implement. All you got to do is to have some bias value. Typically, this sort of bias values are exposed to the end user because it's going to be scene dependent because of our floating point representation, the floating point representation we're using. The bias we will need will depend on the scale of the scene. So depending on how large the numbers we're using for representing all these positions. If everything is in small scale, the bias should be small. Everything is large. If everything is large, the bias should be large because our error is going to be large if we're dealing with larger numbers. So this is going to be sort of scene dependent. Depends on the scale of the scene. But we're going to pick some bias value. And here's how we're going to use it. It's going to be super easy. So where we're tracing this ray, and let's say we found a hit. We found a hit at some t value for the ray. Remember the t value for the ray equation? Any position is p plus t times d being the ray direction, right? We found some t value. We found a hit at some t value. All right. So normally what we do is that if that t value is smaller than 0, we will ignore it, right? That means it's behind the ray. Or maybe I should say smaller than or equal to 0. We'll ignore it. Instead of doing this test, which we already do, we're going to be doing this test with some delta, right? Some value. In this case, this delta is a small positive value that's going to be our bias, right? So we're going to ignore this bit. Now, it is important that this should not be too large because obviously if it is too large, I'm going to ignore some shadows that actually do exist, right? I'm going to start seeing wrong things here. I'm going to be ignoring some shadows that I should be counting. All I want to do is to move this just enough so that all of my points that fall inside the surface because of numerical imprecision is going to be outside of the surface when I'm tracing, right? Effectively outside of the surface. So it should be a small value. It's important that it's small, but it will be scene dependent. But it shouldn't be very large. Oftentimes there's going to be a wide range of possible values. This is not going to be very sensitive. If this is not too large and if it is not too small, it's going to work out. So you just need to pick a value that will be okay. Not a very sensitive value, but you need to have some bias, right? And if you add this bias, then things are going to work out, and we're going to have this nice looking shadow, and everything's going to be fine. All right? Now we don't have these funny streaks anywhere. These points are not shadowing themselves. That was the problem we were having before. All right, so I talked about this in the context of ray tracing. I'm saying we generate a primary ray here, we find a hit point, and then we trace a shadow ray. But ray trace shadows is not specific to rendering using ray tracing at all. Like you need to have some ray tracing capability so that you can compute the ray trace shadows. But your primary rays, they don't have to be computed. Your primary visibility does not have to be computed using ray tracing, right? So I could be using rasterization to generate the image. It's just that when I'm looking at a point, I'm just going to be tracing a shadow ray to find a hit point. For my camera visibility, I don't have to use ray tracing. But for computing shadows, I am using ray tracing. That's why I'm calling this ray trace shadows. All right, so what if I can't do ray tracing? What if I'm rendering on the GPU using rasterization and my GPU, let's say, does not have ray tracing capability? We have a lot of GPUs out there on the market that do not have ray tracing capability. What do we do then? Is there anything we can do? Now, we talked about how important shadows are, right? And without shadows, we don't get the proper orientation between objects. So we need to somehow figure out a way to compute shadows. So even though our topic for today is ray tracing, and I've already explained to you how to do ray trace shadows, we're pretty much done about with this topic. But I would like to tell you a very, very popular alternative technique to ray trace shadows. So how can I compute shadows without ray tracing? So here's the problem. Again, I'm rendering using rasterization. Remember rasterization? With rasterization, the problem is I'm getting my scene data one triangle at a time. So I have this one triangle. I'm going to project that triangle. I'm going to draw it on the screen. All right. So tell me, for any fragment shader for this triangle and for any point on this triangle, is it in shadow? I don't know. I don't even know if there are any other triangles in the scene, right? So rasterization does not help me at all. Like with ray tracing, I just trace a ray, but without ray tracing, rasterization is not helping me. Oh, guess what? There was another triangle, and the triangle was there. Okay, now is this triangle in shadow? I don't know. I have really no way of knowing. Actually, no way of using rasterization directly to do this. But we've been rendering with rasterization for decades, and we've been computing shadows. How on earth are we doing this? Here's how. So there's a very, very popular technique. Very, probably more popular than ray trace shadows. This is possibly the most commonly used technique for computing shadows in computer graphics. That is shadow mapping. A very, very simple idea, and that's the reason why I wanted to just briefly talk about this, so that you guys know that this exists and that you have some idea about how it works. All right. So here's what we do with rasterization without having the capability of ray tracing. Here's what I do. I'm going to take this light source, and what I'm going to do is I'm going to figure out where I have shadow in the scene. Now, we talked about this. If the light source can see a point directly, then that point is not in shadow. If the light source cannot see that point, then it is going to be in shadow, right? So I just need to figure out whether or not my light source can see that point. That's the idea. So to do that, I am going to put a camera instead of my light source. And I'm going to render an image. I'm going to render an image from my light source, right? Let's say I rendered an image from my light source camera, and it looked like something like this, right? So when I'm rendering from this camera, all I need to do is that when I check, is this marked point in shadow? I need to find where it corresponds to on this light image. And if the light can see that point, that means it's not in shadow. If the light cannot see that point, that means it is in shadow. Well, to decide that, I don't need to have a colored image like this for my light view. What I need is only and only the depth map. So the depth map will tell me for each one of the points on this image, the depth map will tell me how far that point is from the light source, right? So with shadow mapping, it starts with rendering a depth map, or what we call a shadow map, from the view of each light source. So each light source will have its own shadow map. And then I'm going to use that shadow map to compute my shadows when I'm finally rendering from my camera view. All right, so it's like a two-pass algorithm. I first generate this depth map by rendering an image from the light's perspective, and then I am actually rendering my main image, the one that I actually want to render. And when I'm doing this, for any point that I'm interested in, I check where that point lies on camera's view, and I figure out the depth value here, and I check the depth value to the distance from this point to the light source. So if there's something that is closer, the depth value here is going to be closer. In that case, I'm going to say, oh no, I can't see this value. It is in shadow. Otherwise, I'll say, okay, I can see that point, so it's not going to be in shadow. So shadow maps are going to have a whole bunch of issues. One issue is that I need to render the shadow maps before I can render my main image, right? So it's going to be a two-pass algorithm. If I have multiple light sources, then for each light source, I'm going to be rendering a separate image. It's going to be a little bit of an issue. You know, also I need to have the right field of view for this light source. It's a spotlight, then it's okay. It's a point light illuminating in all directions. That's going to be a little bit tricky, but not too tricky. It can be handled. This is going to be a raster image, so its resolution is important, right? If it's not high resolution enough, then my shadows that I'll be computing, they're going to be like jaggedy. I'm going to see pixelated shadows here because my shadow map does not have enough resolution. So there's going to be, you know, all sorts of issues like this. But in the end, you can think of a shadow map as pre-computed shadows. And generating a shadow map, it's not doing any shading, right? It's just computing the depth map. Generating a shadow map is actually very fast. And it's pre-computed. And at any point when I'm checking the shadow, it's just a lookup, right? I'm just look up the value in the shadow map, and that's it. So this is very fast to compute. Shadow map generation is fast, and then shadow computation using shadow maps is very fast too. So this is a very, very efficient, very, very fast algorithm. And that's one of the reasons why shadow mapping is still used a lot today. Even in offline rendering, we sometimes prefer using shadow mapping because it would be, in a lot of cases, not in every case, but in a lot of cases, it's going to be significantly faster than ray trace shadows. Even today, this is probably the most popular, I'm going to say popular in the sense that it's used more often, the most popular method for computing shadows. But, you know, ray trace shadows are catching up because our computers are fast enough, and ray trace shadows have fewer issues there. They generate nicer and crisper shadow edges and stuff. So people prefer using ray trace shadows. Also, shadow mapping is only going to work for spotlights and point lights and directional lights. And with all other light sources, more realistic light sources like area lights and mesh lights and things like that, we won't be able to use shadow mapping. But there are ways to use ray tracing to compute shadows from area lights and stuff. We're going to talk about this just briefly next time. So ray trace shadows is actually a more general concept that can be applied to a whole bunch of light sources, and that's why it's becoming, that's another reason why ray trace shadows are increasing in popularity. I still think shadow mapping is probably the most common way of computing shadows today, but ray trace shadows are catching up for good reason. The question here, so if a light source in the scene is moving, then do we need to render new shadow maps? Yes. So yeah, if the light source is moving, you need to recompute your shadow map. Also, if anything in your scene is moving, you need to recompute your shadow map. Right? I mean, maybe the light source is the same, the camera is staying the same, the plane is staying the same, but the sphere is moving. I need to recompute my shadow map, right? So I can't rely on my previous shadow map. But if everything is constant, if nothing is moving except for my main camera, then I can render my shadow map one time and just use it. Like it's a static scene, the only thing that moves is the camera, this main camera, then I don't have to recompute my shadow map. So this is shadow maps. I just had to talk about this because, you know, this is how we normally compute shadows. But if we have ray tracing capability, we can just use ray trace shadows. It's a lot easier, it's a lot simpler, it has fewer issues, and that's exactly what we're going to be doing for our next project. So when we're computing shadows, we're going to be computing those shadows using ray tracing. All right, let's move on. We're doing ray trace shadows, and we'll do that, right? Simple enough, ray trace shadows are a lot easier. We're done. We're done with shadows. No more shadows. Let's talk about reflections. That's another thing we could do with ray tracing that makes ray tracing really fun. All right, that's another nice thing that we will be able to do with ray tracing. So, what are reflections? You must have seen reflections before, right? So you know what they are. But what are they really? I mean, yeah, reflections. This is like mirror, and I'm seeing things. But what are they? Remember when we talked about the diffuse component and specular component of a material? I told you that the specular component was the reflection of the light source. Remember that? Like we're shading the surface, and the specular highlight that we see, I told you that it's the reflection of the light source, right? So, and it is true, it is a reflection of the light source. And when we talk about reflections, though, we're talking about the reflections of other objects, not just the light source, but other objects, right? So, wait, what does that really mean? Let's put it in this context, in the context of the rendering equation. Remember this equation? This scary looking equation if you haven't seen it before, but if you've seen it before, it probably makes sense to you now. We talked about this. So this was an integral over all possible directions, and light is coming from all directions, and we multiplied by the cosine term and the VIDF, and basically this, right, light is coming from possibly from all directions, and we're just doing an integral over all directions, and we were figuring out how much light is reflected in this direction that we're interested in, right? So this was the rendering equation. And of course, in our practical implementation, the light, yeah, it can come from all directions, but it was only coming from the light sources, right? So that's what we were interested in. But in reality, now here's a thing that I'm probably going to repeat a few times. In reality, light does not just come from the light sources. Yeah, light can come from other things too. I mean, if light only came from light sources, we would only be seeing the light sources. We wouldn't be seeing anything else, would we? Right? I mean, what is this camera doing? Or what are our eyes doing? They're seeing light, right? So if the light is only coming from the light sources, I cannot see anything else but the light sources. Obviously, light is coming from other things, like the reflected light off of the surface of this point. That is light, right? And this is light as much as whatever is coming from the light source is light. So light that is reflected off of surfaces like this can be used for illuminating other objects. This whole concept of objects reflecting light and illuminating other objects, this whole concept is what we call global illumination. It's a very, very important part of generating realistic images. This rendering equation accounts for that. So the rendering equation is not just about light coming directly from these light sources, but it's also about light coming from other objects that are not light sources, but they're reflecting light, right? So they're receiving light from the light sources and they're reflecting it. And that reflected light is being reflected off of other surfaces and then reflected off of other surfaces, and then that can also illuminate. So like light can bounce around in the scene many, many times, and then we can see it. But at this point, that's not quite what we're interested in. I just wanted to clarify this point that light is coming from everything and illuminating this point. And we are in general interested in the reflected light off of this point that includes everything, like all the light coming from all objects, light sources, non-light sources, everything over this hemisphere. We're normally interested in all of this to generate a realistic looking image. But what we're specifically interested in right now is a very, very small component of that. What we're specifically interested in is light coming from this perfect reflection direction. We're going to assume that this surface is like a perfect mirror. Now it's very smooth mirror, and we're interested in these mirrored reflections. So it's not going to be as complicated as this whole story that I'm telling you, because we're going to be looking at a small part of this. And we're going to talk about this general story a little bit later. So don't worry about that. We're getting there. All right. So what we're interested in these reflections, right? These nice looking reflections off of this flat surface. What we're interested in is we're interested in these specular reflections, right? Nice specular reflections. I told you specular reflections were the reflections of the light sources, right? So these are going to be the specular reflections of other objects. Specular reflections of other objects. Actually, I'm going to put one more adjective here. It's going to be perfect specular reflections. Perfect specular reflections of objects, right? Not light sources. Perfect specular reflections of objects. So that's what I mean when I say reflections. So what do I mean by perfect? Like what would happen if these were imperfect reflections? If these were imperfect reflections, they could look like this. They could be blurred a little bit, right? For most surfaces, if the surface is not perfectly smooth, if there's some roughness to it, the reflections off of that surface is going to get blurred a little bit. That's what happens for a lot of real materials. But that's not what we're talking about, because computing this is a bit more difficult. We're talking about a very special case. In that special case, I am going to be interested in these perfect specular reflections, meaning this is going to be a perfectly smooth surface. All right? That's what I'm interested in. And let's see how we do that using ray tracing. So here's my setup. I have my camera. I'm looking at a point. I have this point. This is my view direction, omega O. And LO is the light coming from this point towards my camera. That's what I want to compute. And when I do regular shading, what do? I look at where the light is coming from. This light is coming from this direction, right? I figure out how much light is coming, and I do my shading. I figure out the reflected light, and I'm done. So this is the equation, right? So the outgoing light here is the sum of all light sources, and for each light source, I figure out how much light is coming, multiply by cosine term, and then multiply by our surface BRDF. That this is our surface material property. Okay, all good? This is what we've been doing. Okay, so what if this is a kind of surface that has sort of mirror-like reflections? What happens then? Then I will be seeing other objects on the surface, right? On the surface, I will be seeing other objects too. So, but what do I see? To be able to figure out what I see, I can just trace another ray. That is, I can trace a reflection ray. So a reflection is going to be the reflection of my view direction. So this view direction, I need to reflect that vector, and I need to find the reflected view direction. That's where my reflection is going to come from. My perfect reflection is going to come from. And that vector, of course, has the same angle with the surface normal as my view direction, right? And the way we compute this is, remember how we did this? We talked about computing reflections of this light direction, right? When we were talking about the foam material model, we talked about how to reflect this light direction vector. It's going to be the same thing. I'm not going to go into the details of that, but if you're wondering where this equation came from, check out that discussion about how we computed the reflections of the incoming light direction when we were talking about the foam material model. This simple equation, this simple vector equation, will give us this reflection direction. All right, so what do? What I need to know is how much light is coming from this direction. So I'm going to say, for my simplified shading model, light is coming from my light sources. It's also coming from this perfect reflection direction. So I just need to know how much light is coming from my perfect reflection direction. I call it here LR. Right? So what do I do with it? Well, this is very much like a light source, right? Very much like a light source. So I need to do I need to treat it as very much like a light source, and I can just use it like this. But it's a little bit tricky because I am only looking at perfect reflections. So that means I'm going to make some assumptions about my BRDF here for the purposes of handling these reflections. So if these are perfect reflections, they're not going to have any diffuse components. They're going to only have specular components. And that specular component will only work in the perfect deflection direction. So my specular exponent, if you think about this as a foam material, the specular exponent is going to be infinity. So it all simplifies down to something very, very simple when you're dealing with perfect reflections. It becomes this. So incoming lights from the reflection direction, just multiply by some material property. All right, some constant material reflection coefficient. This is going to be Kr, and that will be it. All right, so that's typically how we handle reflections. And this Kr, now it's all hidden here. Specular reflections of objects. The Kr, this Kr property, most software will allow you to set this however you like. But a reasonable thing to do for Kr would be using the specular reflection coefficient as this value. So if I'm using a Blinn material model or a foam material model, let's say in Blinn material model we have diffuse reflection coefficient, we call it Kd, a specular reflection coefficient, we call it Ks, and we had a specular exponent n. So in this case, you can think of this as we're assuming that Kd is 0 or black, and Kr is going to be the same value as Ks, the specular reflection coefficient, and this reflection coefficient. It's still the specular reflection, it's still about specular reflections, so it should probably be the same value, right? It's a reasonable thing to do. And because we assume that the specular exponent is infinity, this cosine phi term sort of disappeared, we're left with this. So this Kr, if it's not given to you, it's a reasonable thing to use the specular reflection coefficient as just the reflection coefficient for other objects. Because it is still specular reflections, right? Just specular reflections of objects, not the light source. But I'm going to talk a little bit more about this when we're sort of generalizing this whole concept to more types of reflections that are not necessarily going to be perfect. But for now, we're talking about perfect reflections. So it simplifies down to something like this. Okay, that's very good and all, but I didn't tell you how to compute this. I mean, this is going to be given to you as your material property. It's the specular reflection coefficient. What is this? Where does this come from? Here's how we compute this guy. What we're going to do is I generated this reflection ray. I am going to compute this, whatever this value is, by tracing that reflection ray. And I'm going to trace that reflection ray, and hopefully it will hit some point in my scene over here, right? It's going to hit some point. And presumably that point is on some surface with some surface normal, right? So what I need to do is to find the reflected light off of this point. That's what I need to do. So how do I do this? I do shading at this point, right? So I'm going to do exactly the same shading that I was doing before. So in this case, my view direction is going to be this, right? This is my view direction now. And this reflected light, the reflected light in this view direction is going to be equal to this coming reflection light over here, the incoming reflection light. Right? So I just need to compute this. That means I just need to do the same shading that I did, but on this point, this side. So that's exactly what I'm going to be doing. I'm going to be computing on this point. So how do I do that? I look at the light sources and I figure out how much light is coming to that point, and I do my shading by looking at all the light sources. It's the same equation as before. It's just that, this is at this point, right? So this material is that material. See, I'm done. That's it. So that's how I compute reflections. I start from here, I generate the reflection direction, I trace that ray, I do shading over here, and then from that shading, I get the light coming from here, and this whole thing becomes this value over here. I just add it to my reflection over here. I'm done. I'm done. I'm done if I don't have any reflections on this surface. What if I have like mirror-like reflections on this surface now? What do I do then? Very easy. I'm just gonna do the same thing over here. I'm just gonna generate the reflection direction here, and I'm gonna trace that ray, right? And figure out what that hits. And I'm gonna do the same computation of, if it hits a point, I'm gonna do the same shading computation at that point. I'm gonna figure out the light that's coming, and then I'm gonna multiply by the reflection coefficient of this surface. And then I'm gonna use all of that for this. So I may have to do this. I may have to do this a few times because, that this reflection ray can bounce around. This blue reflection ray can find another hit point. And the other hit point can be on another surface that has these perfect reflections. So it can reflect again and again and again and again and again. Actually, you know what? It can even go to infinity. So this is not going to be very good, right? Infinity is not good. If you haven't realized it by now, it's pretty bad for a lot of computation. So I need to limit this. So I can't just let my rays bounce around to infinity, because my rendering will never stop then. So I'm going to limit this. I'm going to put a maximum limit. And if I reach my maximum limit, then I'm going to say, you know what, at that shading point, I reach my maximum bounce, maximum ray bounces, reflection bounces. I'm going to say, no more reflection rays. We're done. We're going to ignore the reflections there because I have to stop at some point. So that's how we're going to handle this. Right, so not too difficult actually. Here, the only difficulty as compared to just computing shadow rays is, I generated a reflection ray this time using this equation, and I traced that reflection ray, and I had to do another shading here. And this is sort of like a recursive process. So I need to do a shading, another shading, another shading, another shading. Implementing all this using some recursive functions is fairly straightforward. Unfortunately, though, when we're doing project 6, that's going to be our ray tracing project, for which we're going to have to implement some sort of reflections as like a recursive function, right? So I'm trying to shade this point. I generate this reflection ray. Oh, it finds this point. Now I'm going to shade this. And after I'm done with shading this, then I can complete shading this point. So normally, it's the easiest thing to do is to implement it using some recursive function calls. But for our project 6 with WebGL, we won't be able to do this with recursive function calls simply because WebGL doesn't support recursive functions. But no worries, you must have seen this in other CS courses before. You can take any recursive function and convert it into a loop. And that's what I've done for you. So the code that I've given you for project 6 actually includes a for loop that's outside of shading that sort of handles the reflection component outside of the shading. It just, you basically add this piece after you do the shading for this part, right? So this part is sort of removed from the shading computation because we couldn't do recursive calls. just an implementation detail about the upcoming project. Alright, so we were talking about bounces. My first bounce was from this point, and when I compute the next reflection is going to be my second bounce, and if this ray hits another point, maybe I'll have another bounce there, and at some point I'm going to have to stop, so there's going to be a limit. Let me show you what it does. In a lot of cases, after a certain number of bounces, it's not going to be that important. For example, if you look at this scene, I have some spheres and very nice reflections on these spheres, right? You see the reflections? You don't see the reflections? You can't see the reflections because my bounce limit was 0, so I couldn't do any reflections here. So, by shading these points, I reach my bounce limit of 0, so this sphere's got no reflection. So if I let them have one bounce of reflection, just one bounce of reflection, I will be able to see reflections of the sphere. So now I'm seeing the reflections of the spheres on these spheres. Very good. But these reflected spheres don't have any reflections on them, right? Because my bounce limit is 1. So if I increase my bounce limit to 2, I am going to start seeing reflections on these reflected spheres, right? So I'm starting to see reflections on these reflected spheres, but I don't see reflections on the reflections of the reflected spheres. So if I add another bounce, I'm going to start seeing those, right? Bounce limit is 3. You see, like, relatively fewer pixels are being impacted by this choice. And if I add another level of reflections, some pixels changed. Can you see a few pixels are changing here? Well, more than a few actually. But it's kind of becoming harder to see. From 4, I can go up to 5. Do you see any difference? Well, if you pay attention on this red sphere, reflections on this red sphere, you can see some differences, but it's very, very hard to tell, right? So as your bounce limit goes higher and higher, you're going to have fewer and fewer pixels that will actually need that many bounce. So at some point, you could say that, oh, it's okay to be inaccurate for a couple of pixels here. Most of my image is done, so I'm just going to limit it to something. Next project will have this feature as well, because without it, our rendering may not ever converge, so we kind of need to have a limit, right? And also, no worries, WebGL will sort of require you to limit your loops. And this is how we're going to limit our loops. Alright, so this is the whole conversation about reflections. So today we talked about shadows and reflections, but and another thing that we can do with ray tracing fairly easily is refractions. Refractions are not very different than reflections. The only difference is the direction of the ray that I'm tracing. If I have refractions off of this surface that I'm shading, that means that this is like a semi-transparent surface, right? So this light is going through this surface. I can actually see through this surface. This is the surface of my material, so there's an object underneath this plane, and there's sort of like air above this plane. So if there's an object underneath this plane, it's probably going to have a different refraction index. That means this light that goes in here is going to refract, right? So I need to compute that refraction direction. So I compute that refraction direction, whatever it is, and then I trace that ray and figure out what it is and find out how much light is refracted, and this is how I can add refraction. So computing this is just a little bit more complicated. Not too hard actually, but it involves the index of refractions for the two mediums here, like the air and the object. I'll skip the details of that. We actually talk about this quite a bit extensively in the ray tracing course. We do all sorts of things about ray tracing and realistic rendering and all that. And in the end, we have a teapot rendering competition in which you can showcase the kinds of interesting things you could do with your ray tracers. An example is here. This is an image rendered by Jacob Heidel, who won the last teapot rendering competition. And here he's showcasing a refractive, triangulated Utah teapot using diamond as the index of refraction. And this is actually spectral render, so you can see some color variations in these refractions, which is what happens in reality. This was actually just one frame from a very nice video that he rendered. But the point that I'm trying to make here is that computing refractions are not too difficult than computing reflections. Basically the same concept. You just trace a ray in a different direction. All right, there's a few more details, but still the concept is very, very similar. All right, so I'll leave the discussion of refraction here for the time being. All right, so we talked about reflections, refractions, and shadows in the context of ray tracing, and I want to conclude today's lecture by talking about different ray types. Now that we've seen all these different rays, I just want to emphasize the differences between these different types of rays. So, what are the types of rays that we have when I say ray types? Well, we have primary rays. If we're doing the primary visibility from my cameras, we have primary rays generated from our cameras. And we said any ray that I generate elsewhere, I'm going to call it a secondary ray. So primary rays are the rays coming from the camera or coming from our eye, like whatever for the primary visibility. All other rays that I'm generating are going to be secondary rays. So secondary rays could be used for computing reflections and refractions. I can call them reflection and refraction rays. Or they could be shadow rays. These two types of rays, reflection and refraction rays and shadow rays, they are fairly different types of rays. So these reflection and refraction rays, sometimes we call them like regular rays, normal rays. These are not very different than my primary rays. The only difference is where they originate. If they originate from the camera, I'm going to call them primary rays. If they originate at another point, I'm going to call them secondary rays. But there are going to be normal types of rays. Right? And these shadow rays are going to be somewhat different. And here's why. With these reflection and refraction rays, when I generate a reflection ray, I am going to trace that ray all the way to infinity. I'm going to trace that ray all the way to infinity. That means I'm going to trace until I find a hit point with something. And if I don't find any hits, then it's fine. If the ray goes out of my scene, then I'm not going to find any hits, then it's fine. But I am not going to stop until I go out of my scene. That's why I'm calling it trace to infinity. But with shadow rays, it's not quite like that. With shadow rays, the question is there anything between this point and the light source? So I'm going to start from that point, and I'm going to trace all the way to the light source, and that's where I'm going to stop. Because I don't care if there's any other hit beyond the light source. Like after I reach the light source, I don't need it anymore. So it's going to be different in the sense that I'm going to stop when I reach the light source. Any hits beyond the light source, I don't care. I am not going to look at it. That's one difference. The other difference is that with reflection and refraction types of rays, I would like to find the closest hit point. Right? So I generate a ray, I'm tracing it, I'm going to find the first hit of that array. I don't care if there are any other objects behind it. Right? All I care is the very first hit. When I find a hit, I need to make sure that it is the first hit. It is the first object that the ray intersects, moving along in that direction. And that's going to be important. So if I'm not sure that I found a hit, but if I'm not sure that it is the closest hit, it is the first hit, then I need to continue looking at other hits. If there's any potential that I might be able to find closer hits, then I need to check that. Now, let me repeat this. Let me repeat this because this might be a bug that some of you run into when you're implementing Project 6. When I'm tracing reflection rays or primary rays, I need to make sure that the hit that I found is the closest hit, is the first one along the ray. If I'm not sure, I need to continue checking all possible other intersections with other objects, because maybe I'll find the closer hit, right? It's very important that I find the closest one, because that's the one that I'm going to be shading, right? But over here, with shadow rays, I don't care. I found a hit. There exists an object between this point and the light source. I don't care that the hit that I found is the closest one or not, because I don't care. I was just checking if there's anything between the point and the light source. If there's anything at all, I'm done, right? I don't need to find the closest one. I just need to check if there's one at all, right? So this actually simplifies things quite a bit. When I find a hit, I can say, okay, I'm done. I found a hit, I'm done. I don't need to check anymore, right? That's going to be a little different, because I'm not going to do anything else with that point. But with reflection refraction rays, I am going to need the hit information. I'm going to need to know what point in the scene I hit. Like, what was that object? What's the material on that object? What's the surface normal? What's the barycentric coordinates? I need all these hit information, because I am going to shade that point to compute the reflection and refraction, right? I'm going to shade that point, so I need a lot of information about what that hit was. What did I hit? Where did I hit it? What kind of an object was it? I need to know that. But with shadow rays, I don't care. I don't need to know anything about that point. All I need to know that it existed. That there exists a point, and I'm done. I don't need anything else. So because of that, most ray tracers will have a separate routine for handling shadow rays, because you can handle shadow rays much more efficiently than the other types of rays. With shadow rays, if you have a for loop going through all of your objects, you can return as soon as you found a hit. And you don't need to return anything. You can just say, yeah, I found a hit. True or false, I'm done. But with these kind of reflection types of rays, I need to find the closest one. I need to make sure that I'm finding the closest one. And I need to record the hit information. And I need to return the hit information as well, right? So tracing these are going to be a bit more expensive. So shadow rays in general are much cheaper types of rays. The other regular rays we use for reflections, refractions, and also primary rays, they are going to be relatively more expensive rays. For this upcoming project, I'm going to leave this part completely up to you. You can have a separate routine for handling your shadow rays, or you can handle them within the same ray traversal routine that you have, which is going to be a bit more expensive than you need to, but it will be okay. So you can do either one, whichever one you prefer. But I just wanted to make it clear here at this point that shadow rays can be cheaper, and you can optimize your implementation by handling shadow rays separately, potentially. Right? So that's all I plan to talk about for today. This is where I'm going to stop. Thank you all for sticking around till the end, and I'll see you all next time. Thank you.